So, my assumption is that you have reviewed this film. You basically know what we talked about. Now, first, there is a file SVM utils. You can use that. It's just for visualization, creating the hyperplanes and stuff like that. So that's already provided on Canvas. Now, so this is there are two versions of SVM we are going to solve. One is the hard margin SVM, which is basically there's no C concept. And all we want to do is that basically to minimize 1 over norm 2 of the norm 2 of the W's, right? To maximize that, which is to minimize this term, correct? So this is hard margin SVM. If you don't have this, right, that's hard margin SVM. If you have that, it's soft margin SVM because you had that C value. Now, the first thing for SVM is that we want to define a cost function, right? Now, when it comes to cost function for SVM, there is, because you are minimizing with respect to W, right? So there is a cost with respect to W, lambda times W, right? The norm of W. And there is the second term, right? Because again, your goal in general in SVM is to minimize without that in hard margin SVM, to minimize that term, correct? So your goal is to minimize W. Why? Because the smaller this W, the better the separation, that margin that you have. That's the whole idea. So if you want to have a cost function, so you need to ignore the second part. You need to have a cost function with respect to W. The W should be part of it, right? So that's one part. The second part is called hinge loss. That's a loss function that we use in SVM. Okay. Now look at the formula for hinge loss. It's an average over all data points, summation of maximum of 0 and maximum of 0 and 1 minus yi W transpose xi plus p. Correct? So look at this shape here. Okay. W transpose x minus b equals 0. W transpose x minus b equals 1. W transpose x minus b equals minus 1. What was that 1 and minus 1? You remember we said this inner line, the line in the center says, I want, there shouldn't be any point 1 distance to my right, 1 distance to my left. Right? That's the one term. So W transpose x minus b equal 1, W transpose x minus b equal minus 1. Okay? So when you are looking at this term, what does it tell you? It tells you you need to calculate 1 minus. You need to calculate 1 minus that term, right? Now this term, yi W transpose xi plus b. If you are correctly classified, you are support vector points. What is this value? 0. There's 1 because you are exactly on the line. 1 minus 1 becomes 0. So you don't have any error. If you are correctly classified in either side, but you are not a support vector, your distance is greater than 1, correct? From either side. 1 minus, this is your distance, right? If your right side is positive, if your left side is negative, correct? If your right side, your yi is plus 1. Plus 1 times whatever is the positive, positive. If your left side means this one. This side, for example. If you're below this, your distance is negative. What is the y? Y is also negative 1. So negative 1 times the negative distance becomes positive, correct? Something positive. So this is greater than 1, correct? So it becomes 1 minus something greater than 1. It's a negative. Maximum of 0 and negative 0. What does that tell you? Any point that is correctly classified, either here, here, or it's a support vector point, this term is 0. It doesn't have anything. So hinge loss is only for points that they are on the wrong side of the boundary, misclassified. What will happen if you have a blue point here, right? The distance for that blue point is negative, but the y is positive, correct? Positive 1 times a negative distance becomes something negative. 1 minus minus becomes 1 plus something, correct? Maximum of 1, something positive becomes something positive, correct? Is not 0, it's 0 and something positive, right? So this becomes, it's no longer 0. So if you are misclassified point, you are getting something positive here. Does that make sense? So this cost function, this is the cost function that we are going to use. It's lambda is plus that, right? Now, if that's the cost function that I want to use, we also say there are two scenarios here. What are the two scenarios? Either y I w transpose xi plus b is greater than equal 1. That means the support vector points and anything correctly classified, right? That's scenario 1. Scenario 2 is that this term is less than 1. Misclassified points, correct? Does it make sense? If this is the case, correctly classified, what is my cost function? J of w basically is just lambda is. That term is 0. If misclassified, my J of w is that term 4, which is lambda w2 plus maximum of 0 and 1 minus yi. Plus, that's the same. So you see, you have two scenarios. If you want to code this, there are two scenarios. Either yi times this is greater than equal 1, we use this cost function, or is less than 1, we use this cost function. Correct? Based on which one you use, if you want to take a derivation, you have two sets of derivation. For the first one, if you take a derivation, J with respect to W, what is that? 2 lambda W, correct? For this case 2, the gradient of this with respect to W becomes the same thing, plus, we take a derivation of the second term with respect to W is minus yi times xi. So it becomes minus yi xi. But you also have a b, because there's a b term in the second one, right? What's the derivation with respect to b? Minus yi. That's all we need. Two cost functions, two cost derivatives, right? Is that clear so far? Yeah? Okay. So, now, how do we update? We simply do gradient descent. W minus learning rate times the gradient term. Those are the gradient terms for W and B. Okay, that's how we update it. Now, we started with hard margin SVM. Okay, so let's call this class SVM. Okay, can you use a read, or you want to make it larger? Is that good? Yeah. Okay. So class SVM. what parameters do we need for this hard margin SVM? Look at here. We need a learning rate, correct? Because we're going to do gradient descent. We need a lambda, right? Because again, this one, we had a lambda here. Then let's see what else do we need. Because we do gradient descent, what else do we need? We need a maximum iteration, right? So let's just start with these three parameters. Let's say lambda parameter, that's a float. Then we will say that learning rate, float, max iteration, that's integer. Okay. Then all we need to do is that to define a fit function. This fit function gets an input value and the vector target value y, x and y, right? Okay, what is the first step in SVM you will take? Lagrange. No, first step.
Changing the labels to
exactly. You need to convert y label to -1 and 1. Maybe it's by itself, it is, but you need to have a condition to check it or to convert it. You know, it doesn't matter. So you can say y equal np where y is less than equal 0, converted to -1, as 1. And now this is your new y vector that we are going to use. So, well, now think about it. What is the first step? Because all you need to do is a gradient descent, right? Update W's with respect to gradient. But before doing that, you need to figure out, are you 1 or you are 2? Which one, which scenario you are, correct? So what you need to do is that write a loop through the maximum iteration for the gradient descent. Like
okay, here's what I found.
Okay, we're going to say that for, let's say whatever, in range of, just put a TQDM, range of self max iteration. The class. Then the next thing is that so first for loop is for loop with respect to max iteration for gradient descent. The next loop is that you need to look over each data point and see if you correctly classified it or not. Right? So you will say for example, index and xi in enumerate x. I'm looping through the data points that we have one at a time. I get the index and the value. Enumerate, that's what it does. Then you need to check 1 or 2. So we are going to define something called condition. And the condition is that if this is greater than 1. Right? So I would say that the parameter condition. And I would say that if y index times y times this value, right? Open a parenthesis, W transpose xi. So we can say that np dot matmul x I and self dot w. Okay. We don't have self dot w actually. Let's here at the beginning. Because we want to do gradient descent, we need to randomly initialize the w, right? So here, initialize your w randomly, self dot w, np dot ones, for example. How many we have? X. Actually, this is one thing I'm going to do. N and n features called x dot shape. Then here I will put n features. So, and then also we have a B actually, self dot B. At the beginning, I will set it to 0, bias there. So here I would say NP matmul W transpose XI plus self dot B, correct? times that y value should be greater than equal 1. So this condition multiplies this, checks it. If it's greater than equal 1, it becomes true or false, right? So if it's true, that's your cost function. If it's false, this is your cost function, correct? With respect to that, if it's true, that's my gradient. If it's false, these two are my gradients, right? So we will say if condition then update self dot w minus equal self dot w becomes self dot w minus the gradient, right? What is the gradient? 2 times self dot learning rate times, because this comes from here. Look at here. W becomes W minus learning rate times the gradient. That's the gradient, 2 lambda W, right? So self dot times self dot lambda times what's that with W? So self dot W.
Cannot ignore that too.
No, because we took it to the power of 2. You need to always have that 2, because otherwise, known 2 doesn't have a power of 2. We take it to the power of 2, always to the root of the square root. So with derivation, you need to be sure that they cancel each other out. So else, basically, now that means you are in the second scenario. So you update your W using the same thing, minus yi xi, right? That becomes, this should be inside the parentheses, because that term is the gradient together, right? Times the learning rate.
Then 2 has to be minus 1.
2 being multiplied by which part? Let's see, 2 lambda, right? You're right. So 2 will come 2 times self dot lambda W minus that term. Okay, then you go for B, self dot B minus equal, what was the value with it? Minus y. Minus y. Yes. Correct? But that's all you need to do, is that basically look through this for each data point, basically see where you are, based on where you are, update the W and update B if necessary. So let's run this. Say model equal SVM. SVM as an input requires a learning rate. Let's put 001. Require max iteration. Because it's expensive, let's just start with 500 and equal lambda. Now, it will require some data. We need to import some stuff here, I think.
Reason. Derivation. That cost function of B, should it be multiplied by the learning rate?
Let's see, maybe, let's see. Yeah, you're right. We're gonna do that. Let me first fix this one.
Yeah.
Six. This one, that is correct. So this one times that
Yes.
is correct. Okay, so run this. We need to generate some data. Data sets dot make blob and samples. Let's see, 1,000 sample and features. There's 2 features. Centers 2. We're just generating some random data. Okay. So next step is that we're going to call model.feed and pass x and y to it and let it run. It's y.
So that math.
Y doesn't have an index, right? Y is just, so you need to add an index to y. So here we would say
The order of matrix matters, right? Should be yi into x.
y is n by 1, 1 by 1. X is, let's see, not. Dimension. Why you don't need it?
Because said that xi is a vector and y I dx is a scalar. So numpy just does it itself.
Yeah, so if we do it in p dot, we don't need to do that. So you let this run, then there is a function, it's called within that scalar from SVM. Function called visualize SVM. So this one, you pass the data, you pass y, and you pass the model. Basically, plot that for you. Yeah, it's being recorded, so you can just watch this later. What I want you to do is that basically play with the parameters. Okay. Play with the parameters, see the impact of maximum iteration lambda parameter on the basically separation that you will see. And as in this version of SVM, it's fast because all we do gradient descent technically, right? We are not doing a dual SVM. Remember, the expensive one is when you have those lambdas. It's not that expensive because here again, here is just two loops. We do gradient descent, but in the dual SVM, you need to go through all those lambdas and solve them, and you cannot do one at a time, right? Because there you need to do some algorithm, some other techniques. But again, watch the video if you don't have the materials fully ready. It is a recording, so watch it later. But what I want you to do is that to play with the parameters to understand the impact that they have. Okay. One other thing you can do is that for the same data, call to scikit-learn linear SVM and do a comparison between the parameters of your model and parameters that scikit-learn gives you. So you will understand that they're kind of the same. They should be in the same range, basically. So now the next one, solving using sequential list programming. We're going to do soft margin SVM. That means that the first one was a simple SVM. So we are going to do this one. Okay. So for this one, there is a difference. One is that now we have that concept of epsilon, the slack variables, right? And remember this as epsilon. For any point that you are correctly classified, epsilon is 0, right? 0, 0, 0, 0, 0. This point here, this is correctly classified, but within the margin. It's going to have an epsilon between 0 and 1. This point is misclassified, the other side of the margin, going to have an epsilon greater than 1. So you need to remember those ones. Then, yeah, this is going to be the cost function that basically we have. This cost function here, you need to remember, has constraints. This is one constraint, this is the other one. And when we went to the Lagrangian form, let me pick this. So our goal becomes to maximize with respect to alphas, summation of alpha I 1 minus 2 I j alpha I alpha j y j xi transpose xj, right? This was the dual form, right? Subjected to we have alpha I less than equals to greater than equals 0. Right? This was the dual soft margin SVM. Right? So for the hard margin SVM, we can also use solving using this technique. There are two ways. This one that we did right now, right? Okay, that's one approach. But do you remember when we did SVM, I said, if your data set, number of data points is less than the number of features, the approach that we right now solve is going to fail. The code that we right now wrote, we did gradient descent, right? That code will fail, you cannot solve if you have more features than more data points. In that scenario, you need to do dual SVM, dual hard margin. And the only difference between dual hard margin and soft hard margin, what was that?
The C.
In this one, the C term. If you remove that, this is dual hard margin SVM. If you put that, that's dual soft margin SVM. So this code that I'm going to write for the dual hard margin, soft margin SVM, you can use it as a dual for hard margin. Just you need to remove the C. That's the only thing you need to do. Okay. So now basically you are learning to do SVM in two ways: gradient descent, which is what we did, and now using that Lagrangian. For Lagrangian, when we get to this point, we say this is quadratic, right? Because you need to find alpha. And it's not that straightforward. You can write a loop, but it's going to take forever. Keep looping through alphas, fix all alpha except one coordinate distance, right? That's going to take time. That's why in the class I told you, there are so many algorithms that they're going to do that job for you, to optimize finding the alphas for you, right? In order to learn that, if you click on this page, If you go to, let's keep it. It has the that optimize. That dot optimize. If you go to that page directly, just this is good for your future, wherever you want to work. There are so many optimization techniques that are already pre-built. You know, any type of optimization that you want to use, they're already pre-built. Just go to the document, read them. They're talking about local optimization, global optimization, convex, concave, whatever, right? Already done here. So if you want to create an algorithm, don't necessarily need to solve that part yourself. You can just go to these libraries. These are math libraries. The companies are okay with using these ones, right? So you can go through these libraries, learn what type of optimization you want, and use it in your problem. For today's class, we are going to use .minimize, which is just a minimization function, because all we want to do, our goal is here to maximize this. But you remember also I told you that it's cheaper to minimize, easier to minimize, always. So we're going to multiply this by negative and minimize the negative of this. Okay. So this minimize is a general optimization function. This you need to understand what does it require as an input. This minimize function, it has as an input, it asks you what is the function that you want to minimize. Negative of this. So this is the function. When it asks you what's the function, negative of this term is the function. X0. What do you think is X0? This class. What's X0? What are you solving for? Alphas. Initial set of alpha. That's X0. That's initial values, right? So you solve for alpha, you need to pass some random alpha at the beginning, right? What is the method? The method asks you that what optimization algorithm you want to apply. So if you scroll down, those are the list of all minimization algorithms that you can use, right? You can read through, they all collect through a paper, they all have their own pros and cons, right? Depending on what is your complexity problem issues. Sometimes some of these algorithms are really good for if you have multiple cores on your CPU. Some of them are good if you have a better number of RAM, like a larger RAM than CPUs. So that's how you decide in industry. You look at the definition of this optimization technique, you look at the hardware constraints that you have. Based on that, you basically select, okay, this top 4 is useful. You do a test across those, see which one is faster, less expensive, and you use that. That's how you narrow this down. For today's work, we are going to use SLSQP, sequential list square programming, right? That's basically all it does. It just sequentially basically try to solve for alphas. Now, what it requires from you after that, so was the method which we are going to use SLSQP. It tells us Jacobian. Well, what's the definition of Jacobian? You are on it. You just said it. First derivative, first gradient. First derivative of a function, also called Jacobian function. So remember that, you know it already. If you go somewhere, someone tells you that, can you calculate the Jacobian? That's just a fancy term, tell you that take the first derivative. If they tell you, give me the Haitian, is the second order derivative. You remember Haitian matrix gives you of a function to a vector gives you a matrix. So this function asks you that, hey, for this, so this minimization tells you for this function, which is this term, that you are trying to solve with respect to alpha. Can you give me the first order derivation of this with respect to alpha? Can you give me the second order derivation with respect to alpha? The benefit of this is that if you provide it to the algorithm, it becomes faster in solving. The algorithm doesn't need to go through it. You tell the algorithm, in each step, do this. So we already have this. So the Jacobian, with respect to alpha, what do we get? There's a 1, basically, with respect to alpha I. Okay? The derivation of this one is 1 minus, what's the derivation of this one? Alpha j times that. Correct? That's the Jacobian, right? With respect to 1 alpha. So, is that clear so far? This minimization function. These are the requirement that this function will ask you in order to give you the alpha. Okay. So now let's write. What do we need for soft margin SVM? When we want to code this, what's the only parameters you need? C. Everything else is X and Y is the data. Alpha you're going to learn, right? So there's nothing else that it requires. So you want C to be a float, and that's it. What's next thing? Okay, next thing we are going to define that function, the cost function, right? So another cost function, the objective function. So we call that define dual SVM, because that was a dual form. So what does that dual SVM wants? This function. It basically has if you think about it, if I want to calculate this value, every time I call to this, I need to do this huge multiplication across all I and j, multiply xj, yj, correct? Does that make sense? Every time you need to do that, every time you call to this function. So if I'm smart, in order to get away from that cost, I'm going to calculate this term, xi, xj, yi, yj, for all my data points somewhere, and I just pass it to this function. And you don't need to calculate it yourself because I only need to do it one time, right? So I assume this function as an input, going to get a value called gram xy. And gram xy, we are going to define it as is summation xi transpose xj yi yj. We call this gram x1. So again, rather than every time we recalculate that, we're going to calculate it one time and keep passing it around. Because that's constant. Xi and yi, they don't change, right? So what else this function requires? Requires set of lambda or alphas. And it needs to basically return minus summation of alpha I. So alphas dot sum minus 0.5 times.
But negative of the.
No, we do that in another place. Alphas dot alphas dot gram xy, right? Because alphas, each alpha is one alpha, but because you multiply by a matrix is a vector of alpha. So alpha dot that matrix. That basically returns that value, correct? The next thing we want a function for derivation of that, right? Because again, remember this minimize function asks for the Jacobian. So we can call this let's say Jacobian or Jacobian or dual SVM. That also requires the same in gram, xy, and alphas. Okay. So now look at here. This derivation that I took was with respect to one alpha, correct? If I do it with respect to all alphas, this becomes an identity matrix, right? Minus that value, basically, for all the alphas. Correct? If we take a derivation of this term with respect to each alpha and sum those together, that becomes with respect to all of them. We want to show it as a vector form. So this becomes return NP dot ones lengths of alphas minus. So look at this one, this term. If you take a derivation of this with respect to alpha, you have alpha dot alpha, alpha transpose alpha. Derivation of that becomes 2 alphas, right? 2 and 0.5, they cancel. So it becomes alpha dot gram xy. Correct? Derivation of this term with respect to alpha. Alpha dot sum becomes an identity matrix, and this one becomes 2 times this. So they cancel, it becomes alphas dot gram xy. So we have that now, then we are going to define a fit function. This fit function as an input get x and y. At step 1, the same thing. We are going to convert y into -1 and +1, right? To be sure that it's correct. So NP dot where. So now we want to use that function, minimize function, to solve this, correct? But there is also a part in this minimize. We didn't go all the way through the end. Here. So after the Haitian, this Haitian P doesn't matter. Here, bounds, constraints. Right? So here, these are constraints, correct? So you need to define this constraint passively. Now, when it talks about constraint, if you scroll down in the definition of the function, this module, with constraints, constraint, you need to pass it as a dictionary, okay? Or as a constraint. So there is a module you can call constraint. We are going to do a simple way. Create a dictionary for each constraint. What does the dictionary require? Constraint is either linear constraint or non-linear. Remember, is either less than equal 0 or less than equal or equal. That's a constraint. If you have a constraint which is greater than, you need to convert it to less than. That means for alpha cannot be greater than 0. It should be minus alpha less than 0. So that's how you need to define the constraint. But what do you need for that dictionary to create? If you scroll down, this is all you need to pass. What is the type? You say either EQ, equality, or inequality. That's the type of constraint you are passing. The second key is function. What is the function? You pass the shape. What's the function? This is the function. This is the function, right? Third, what is the derivation of that function? Jacobian. Fourth argument, if you have additional argument. We don't need that. So that's the constraint. Now, in order to make it easier, because I figured out everyone has a problem with that, I'm not going to pass this as a constraint. Passing this one as a constraint, I'm going to pass this as a boundary. This function also has something called bounds. If you scroll up, bounds, it allows you to define a minimum maximum with a parameter. So you don't need to convert this to minus alpha and write it multiple times. So you simply, for that one, you can just call to the bounds and then pass what's the minimum 0, what's the maximum C. That's it. Every other semester, I was trying to teach a student to do the other one, and it was always back. No one got the concept of Jacobian and everything over there. But anyway, so now all we are going to do is that first define bounds. So we have, we need to import from CircuitPy.optimize. You need to import this one. First is minimize. Minimize. Then you need to import bounds. Then you need to import constraints. constraint, but okay, let's see, constraint. And then we need to import SL. Maybe we don't need that. Maybe that's enough. Let's see if we need anything else.
The Hessian of the objective function, it is simply gram xy, right?
1 second. Minimize bounds string. We don't need that. Let's. So first, let's start with bounds. So you call to this bounds. What does this ask you? So let's see. Basically tells you what is the lower bound, what is the upper bound. Okay. Let's see. Okay. Let's see. Okay. Okay, anyway, enough time for that. So we want a lower bound. So we have how many, because we just don't have one lower bound. Remember, we have n zeros, n c. That this is repeating 2 n time, right? Alpha I, n time less than c, n time greater than 0, correct? So we need to repeat that. I think this becomes something like np zeros. We have n, and then np dot ones. Well, actually, there's a function np dot full as n and self dot c. That np dot full is the same if you do np dot ones multiplied by c. It creates you the same thing. So yeah, I'm going to fix it next. Let me see information. Yeah, that should be correct. And it becomes self dot. So that's bounds. Then you're going to create constraints. And then all we want to do is that we want to create this dictionary. If it has 4 terms, type, function, and Jacobian of the function. So type was equality, right? Then it tells you what is the function that you are solving. The function was what? Minus summation of alpha I, yi equals 0, right? So we have, if we need to write a function there, right? So easiest way is, if we use lambda, so we can say lambda a equal minus a just simply done. We also haven't defined a yet. We need to define a set of alphas, initial random alpha. We will define that later. But in this np dots. Then we have Jacobian, which is the derivation of this function that we wrote. We are going to also write that using lambda. So we're going to do lambda a. And what is the derivation of this with respect to a minus yi, or minus y, correct? So does this make sense? This constraint. You basically wrote this, right? Minus alpha I times yi. But you cannot write it as together. This constraint goes per alpha and then sum those together, right? So we do this a function over each a. A is technically each alpha. And you multiply that together. Or you can think of it as actually the easiest way is that alpha is a vector. Dot product of this vector and y vector becomes minus of that, right? So np dot a as a vector alpha and y is a vector y. That becomes summation of a dot a times y, correct? Dot product of those two vectors. Alpha again is a vector, y is a vector.
Alpha is a vector.
Yeah, alpha. So all the alphas that you have. How many alpha you get?
And
Right. So you get a vector of n, right?
but you said the function as in one by one.
So this is going to be, think about it from the function perspective. You are defining a formula,
Yeah.
right? This function says that whatever is the a you are passing, you need to multiply that a, but y. Y the y, right?
Yeah.
Do you learn alpha one in a one shot? No. You look through it, correct?
Yes.
So in each iteration, you have set of alphas that you want to multiply by that to be sure that those alphas are good. Because if I have set of iteration t equal 2, I have a vector of n alpha. How do I know those alphas are good? If I multiply it by y, summation should be 0. Alpha is changing, but each time you pass a vector of alpha. Okay? So now we want script programming. So we will call to minimize function. What does minimize function require? Ask you first, what is the function? Okay. So function equal self dot dual SVM. That was the function. But so actually, let's do a couple of steps here before we get there. Because all those self dot dual SVM, they require to have this gram XY. We haven't generated that yet, right? What was gram XY? Summation of XI transpose XJ, YI, YJ, right? So what we can do is that we can say XY equal X, you should say X dot Y new axis, and then gram XY becomes XY dot XY transpose. We will see the dimension. I might be wrong, but basically I multiply once XY together and then multiply it again by itself. That will give you the same thing, right? So then the next thing we need is set up initial alphas, right? So we can say alphas np dot once. Let's create that. Let's say n and n features. That's alphas. Now here, this function that we have is per alpha, right? So we need to we don't need to, but let's see. So this function gets as an input gram XY and alphas, right? Then what else does the minimum want? X0. What's X0? Initial set of alphas, right? So X0 becomes alphas, the initial set of alphas that we defined. Then it requires a Jacobian of this function. We already have a function for that, right? So Jacobian becomes self dot Jacobian So and that as an input again gets gram xy and alphas. Right? We defined those functions before, right? We just called this. What else it requires? It requires bounds, the boundary, and the constraint as an input. So we are going to say bounds equal bounds and constraint. So you are telling this function, hey, minimize this for me. Okay. With respect to what? With respect to alphas. Right? What is the constraint? This is what's the boundary?
There is a method also missing in this function minimize.
Oh, yeah, great. SL is great. Then how to solve it? Let's use a method. It's capital LSSQ sequential least square program. Right? So after this is solved, what does it give you? Optimal alphas, right? So we will say that self dot alphas equal SLSQP dot X. Why X? Because this program is solving it with respect to X. X as an input. That's all we say. That's why we call X. Okay, so
we pass the derivative of dualism.
that's great. Give me 1 second. Oh, okay. So for the functions, we also need to use lambda. So here, lambda A. It requires the function to be complete. So this one also becomes lambda A. So the next thing is that this term is a maximization. This function is a minimization. So these two functions need to multiply by a negative, the derivation and the function itself. So you put this a negative here. A negative there. So now, when you have the alpha, what's the next step? To get W, right? W was summation of alpha I, xi, yi, right? So self dot W becomes into what this returns to you, returns rest. Okay, so X is one array. That means doesn't have a dimension 1. You need to add np.new axis as a dimension. So here you want the summation over this np.sum over new axis. We want to multiply that by xy. Already have xy. We already calculated above xy. And we don't want to do summation over that. So np.sum. So np.sum is one of those operations you need to specify axis, right? You want to do basically on the which axis do you want to sum this value? So here you need to say put this together.
What is the gram matrix?
It's not gram matrix. X is 0. Gram matrix is gram xy. Xy is just x times y. So self dot W. Now we have our W, correct? Again, W comes, again, if you forgot, this is W. One summation alpha I by I to xi. Alpha is a vector, is one array, doesn't have a dimension 1, so I added dimension to it. It becomes something n by 1. N by 1 times xy. Xy we already calculated above, right? And then we do a sum over that. We'll give you that summation term basically. Okay, so we have W's, we have alphas. What's the next step? We want to find B, right? But also, how do we find B? Before we find B, we need to find support vector points, correct? So self dot support vectors. So support vectors are which part vectors? Vectors that the alpha is greater than 0, right? When you solve, every other points they have some alphas. If you are correctly classified, you are not important. Your alpha is 0. If your alpha is 0, you don't help in finding W because your alpha is 0. So support vector is any point that has an alpha greater than 0. Now, other libraries and outside, basically, we don't just look for 0. We actually define some epsilon. We say if the alpha is greater than some epsilon, not precisely 0. So we will say that basically x where self dot alphas is greater than some epsilon, and then we are going to define epsilon here. On e minus 6. You just don't want, because you might not exactly get 0, so you just put something a bit larger than 0. So that becomes your support vector points. Now, when we want to calculate the intercept, in class I give you a different formula. Bishop book recommends to use a different approach, which is much faster to find B. Basically, what it tells you is that if you find these points, find the support vector points, okay? And for those support vector points, calculate the distance, right? And say yi, the value, minus the distance, okay? Yi should be -1 and +1, correct? Is that correct? These points should be exactly on 1 and -1 because they're support vector, right? So basically what the book says is that rather than trying to go through the other formula, for each point, find the location, calculate the distance between location and the class value, right? And shift the line by that. So that means that if you find something like this, maybe this is your support vector, for example. Not exactly on the line. You find this gap on average and shift the line by that gap. That's how the bishop is basically. The other way also you can do it, but since this one seems to be giving you a better optimization. Also, I think scikit-learn also I think does this one. So what you want to do is that you want to first find this point. These are the points that have a minimum distance, right, to the line. So we see you want to first find those minimum distance. So we say minimum distance. So do an NP, basically do a think. You first do the distance, then you do the minimum distance. This is just say sign distance. So for distance, what do you need? W transpose xi plus p, right? So do that. Yeah. I did do NP math model NP dot. For support vector points, we already know which one are the support vectors, right? For support vector points, you multiply that by the W. So that becomes, for each of these support vector points, you are finding the location. Right? We don't know B. We are trying to find B. B at the beginning is 0 for us, right? So then you want to find the minimum, basically the minimum of those, like out of the support vector points, because not all of the support vector points are going to be random. Lots of them are exactly on the line, but there are some support vector point, basically, let's say this is correct, this is correct. These two are inside, those are minimum. You find those ones, because those are the ones that you don't want to be there. You want to shift the line somehow that exactly goes over those 2 points also. So you do minimum distance, np.argmin of this sign distance, because it's np-argmin, it's going to give you the index of those points that they have a minimum distance. They're inside the boundary, right? So for those points, find the support label. What's the y value? This becomes y. Why this one?
Yeah.
Self dot alphas is greater than epsilon. So these are the support. See, support vector labels. Okay. Now we want to define that intercept or B. Self dot intercept becomes self dot support vector labels. Okay. For that index, the minimum distance index, minus sign distance for those minimum index. Sign that becomes your intercept. Does it make sense what we do here? We are looking at the support vector points. We are figuring out there are a couple of points, support vector, that you are falling inside. Okay? So those ones, if you look across for this class or this class, they have a minimum distance to the center line. Right? So we find that this one and this one has the minimum distance. So we found the index for this one. Then we are saying that the label of these two minus the distance that they have. So the label for this one is 1. The distance it has, what is it, like 0.9? That becomes 0.1. That's how much you need to shift that line. For the other one, this is -1. The distance is 0.9 because it's distance positive from this line. How much you need to change it basically also 0.1. You basically figure out how much I need to tilt this line to account exactly for those 2 points. So run this. Let's see how much error we're gonna get. So
Then the intercept will be vector.
so is a number.
But the way you are calculating, you get
So in that support labels, you then make it a class attribute. A line above it. I think you need to add that separately.
Oh, that's good. Actually, we don't need that. We will get. Let's run it and see where we get error. That's the easiest way. So soft merging SVM that requires a C. Let's say C is 100. Now we need data. So X train, Y train. There's a function. There's a function in that library that we gave you called generate for data. This tells you how many you want. Let's say n is 1000 and sigma is 0.4, and then after that we can call this plot SVM and pass this X train. Right. Yes. So this is the data that we are creating Because for soft margin SVM, we said, remember the data has class overlaps, right? So hard margin SVM cannot solve for this because, again, these are because of the cost function, especially, this is going to be a problem. So this one becomes hard soft margin SVM. Now you pass this to model.feed. This is element-wise multiplication. That's the first thing. This is an element-wise multiplication. Let's say good luck. And let me make this small, because this is that's great. One thing. Let's plot this, and then we will increase the dimension. But let's plot SVM. This one requires again X train, Y train. You can pass model.intercept or support and support vectors. Model.w, model.intercept. So training data and X, or I need to define an X. So that means you're using PLT subplots. Those parts is not important. I'm just creating an image to so we can print it out. So this becomes basically this two becomes your support vector points, right? That exactly drew the lines on it. When you are looking at the alphas, you'll see that 0, 0, 0, and there are only two alphas basically that are greater than that epsilon. The other ones, they are not zero, but almost zero, minus 16. That's technically zero. That's why we define an epsilon, because you might find support vectors that the alpha points that the alpha is not exactly zero, but they're really small. So don't look for alpha equal to zero. They just we define epsilon, for example, is 0.00001, something like that. Now, if you increase this to 100, let's see what will happen. So now these points becomes your support vector points, and see which one.
Mine outside.
Wait a second, why this line went to the other side? Let's take a look.
So you can
now, so this is the boundary. I don't know why this one fell outside. It's a secret. This should fall in the center. Let's do one thing. So that negative doesn't do anything else. Keep that in mind. Let me see. Either I lose something on. Actually, we can test it out. So let's call to SQLearn. See, we get the same intercept values. If we get the same intercept, then the plotting function is the problem. One called SVC. Say CLF, SVC, kernel. So you say that kernel to be linear because we are not passing any kernel. It's a linear classification that we are doing. Gamma to be auto. You don't need to specify it. And C, it was 100. Right? And then we say CLF that fit X train, Y train.
There is a format slash tag.
So CLF dot we call this coefficient. CLF dot coefficient 0. Oh no, coef 0 you said. Coef underline. There's another prompt in 0. 7224783. 7224788. So weights are, we get exact same weights. Let's go on CLF dot intercept 0.28. That's where we get the. See, the intercept is the one that moves the line, right? We get 3.8. The intercept that on over there we get is 0.2187. So let's see.
Use CLF dot intercept 0 for that plotting function.
No, that's not the goal. The goal is not the plotting part. It's to learn to figure out why the intercept goes wrong, right? But I can review this data. All the codes. I need to figure out why. But you learn the process if you want to do a soft margin SVM, basically, or if you want to do SVM using dual. All you need to do is that formulate the whatever we have, the Lagrangian form. You have constraints. You can either write both of them as constraint. For this one, you can use bounds. It's much easier. And this one is constraints. Then you call to a minimization function, define what type of algorithm you want to use for that minimization. And then basically you solve it. Then you have alphas, you get W's, then you get B. The problem here is that, and that's what you're going to practice, increase this to 1000, for example. Let's see what will happen. I think this is going to run for a while. You need to time it, or maybe it's going to true. So what you want to do is that for your project, some algorithms are expensive. As soon as your number of data increases, it's going to look for a while. What you can do to show, not to me, or even for your project, for yourself to learn that how is the process would work. Don't use all your data. Pick a smaller portion of your data, run the algorithm 1 time, 2 times. For example, I picked 100 data points and I ran it. It took 20 seconds, 15 seconds, right? I timed that. And I also monitor how much CPU I use, how much memory I use. In Python, you can put the code behind this in Jupyter, it tells you how much CPU you use, how much memory. Next time, I go to 1,000 data points and run the same thing, monitor the same information. Is it still running? See, that's how you do cost complexity analysis. So in your report, you say that, okay, I use this algorithm with 1,000 data, I got this accuracy. Okay, but this is the cost of the model. If I go from 100 data point to this data point, time from 1 minute went to, I don't know, 2 minutes. You can find the complexity using that, right? If for 100 data point is 1 minute, for 1,000 data point is 10 minutes, you can find the relationship between the time, right? So you find the complexity of your algorithm. That's what you report that. Then you go to a different algorithm. I have a simpler algorithm. My simpler algorithm, I pass all my data. It took 5 minutes. This is the accuracy. Maybe accuracy is much less than the strong one. Based on that, you describe, okay, this is the cost, but because in my problem, cost is really important, or maybe cost is not important. However you describe it. In my problem, cost is important. I'm going with the algorithm which is cheaper, but it gives me a bit, reduction in the accuracy. That's the goal of the project, not just getting a high accuracy model. I really don't care about those numbers, to be honest. I care about you being able to break down the algorithms on the cost, why you choose them, and make decision. Like assumption, make decision, write the assumption, and basically explain those. Okay, this is, look, from 1,000, it's just gonna go forever. So SVM is really expensive, even if you use a really good algorithm. Okay, so let's stop here. I will take a look at that intercept and I will post something about it. But there's a recording. If you don't have the code, go through the recording.